Hello students, in our previous lecture we learned the relationship between velocity of wave and depth of flow. We also learned that for critical flow any disturbance at a point would not travel upstream because wave celerity would be equal to velocity of flow. We will put this understanding to some engineering application and we will try to solve a problem that how much we can reduce width of the river so that we can build a bridge of smaller span. So the question that we are trying to look into says that a bridge is planned on a 50-meter river and which is rectangular in shape and the flow that it carries is 200 meter cube per second. Flow depth is given as 4 meter and we have to reduce length of a bridge such that upstream water is not influenced for this discharge. So when you build a bridge, you are inducing some disturbance and we don't want that disturbance to really go upstream for given discharge conditions. So here we will bring our fundamental understanding about specific energy and variation of it with respect to depth, variation of discharge per unit width or small q with the depth, and we know that while energy achieves minimum value for given small q equal to c, the specific discharge is maximum or discharge per unit width is maximum for given E at critical depth of flow. We also learned that since E is equal to V square by 2G plus Y, at point where we have minimum specific energy, we take the differentiation with respect to Y and we ended up with the relation that V square upon 2G should be equal to Y by 2, or this contributes half of the head as contributed by the elevation head, which gave us Yc equal to 2 by 3E. Similarly, when we substitute this E equal to 3 by 2 Yc, we can further realize that this point at which discharge is maximum corresponds to G into Yc cube and its square root, and this corresponds to the critical depth of flow where Yc is again 2 by 3E. Another important thing that we must keep in mind is that nothing has been said about change in specific energy or losses that are happening in the channel. So we can assume that if our river is something like this, and this is section 1 and this is section 2, and we want to make a bridge on section 2, no losses are taking place between section 1 and 2, and if at all they are taking place, they are negligible. Also, in absence of any other information, we will take our channel section to be completely horizontal. Now, with this information, let us look into how our detailed calculations are going to look like. So first of all, we will calculate specific energy at upstream. Upstream E is given by V square by 2G plus Y. We know that total discharge is 200 meter cube per second. Width upstream is 50 meter and depth upstream is equal to 4 meter. So we can calculate our E as 4 plus V can be written as Q by A square upon 2G plus Y we have already added as 4 here. So I will just add 4. Our Q is given as 200. Area of cross section is also 200. So this would ease some calculation plus 4, which implies E is equal to 4.05 meter. Now, if this is clear, let us also calculate Froude number at section 1 to ensure that our flow is indeed subcritical. So it comes out to be velocity is 50 divided by 4 into 50 Q by A divided by 9.81 into 4, which comes out to be 0.25 divided by 9.81 into 4. And this of course is less than 1. So that establishes that upstream our flow is subcritical. Now we have just discussed that at critical flow, depth of flow is going to be 2 by 3E, which in this case would be 4.05, and detailed derivations can be accessed in previous videos. So this comes out to be 2.7 meter. So this is going to be an important finding for us, which we will use later. Now, this should be the depth of flow at site where we are building the bridge. Now we know capital Q because continuity is applicable, no change in storage should take place. We now know the depth of flow. Depth of flow comes out to be 2.7 meter. There are two unknowns at this stage because we know that Q is equal to velocity into Y into B, and we are altering the width of flow by constricting this river. What we will have here is that one equation and two unknowns. So if we divide both sides by B, we are going to get small q is equal to V into Y. And we know that at YC, our flow is given by root of GYC cube. So now in this particular solution, we can say that our YC is in fact cube root of Q square by G, which implies our QC comes out to be YC cube into G. So now our QC hence comes out to be 2.7 cube into 9.81, which in this case turns out to be and it's square root. In fact, it's square root because this is QC square. So this comes out to be 13.9 meter cube per second per meter. Now BC, or width of section where we are constricting the channel, would come out to be Q divided by 13.9, or QC, which happens to be 14.4 meter. Hence we can reduce the bridge width from 50 meter to 14.4 meter. In fact, in this case, it would be length of the bridge and width of the river all the way from 50 meter to 14.4 meter without altering the upstream condition. So this is one key application of critical flow, that how this calculation helps us in some engineering calculations. Thank you.